When we're dealing with probability and chance experiments, there are two things that we always need to know. We need to know what could happen and what's the likelihood of these things happening if I want to describe this chance experiment. So together, this is what we call the probability distribution, as what we use to describe our random phenomena. So in this video, we're going to focus on the first one, which is our list of things that could happen so that we know what we might actually have come up. Now, in stats, we call this our sample space, so the list of possible outcomes. I'm going to use a capital S to denote sample space. In other places or textbooks, you might see a capital omega or a capital U for the universe, but we'll be using a capital S. So the way I like to think about sample spaces is I want to pretend that I am narrating a chance experiment. And so my outcomes are what I might possibly narrate to someone when I'm describing what had happened. So, for example, a very simple chance experiment would be tossing a coin 3 times. So here I have a coin. It has 2 sides to it. It has the head side and it has the tail side to it. So I'm going to flip my coin and we will get tails, tails, heads. So I said out loud, tails, tails, heads. Now, we aren't obligated to write out the whole entire words. We can use shorthand. So if I wanted to shorthand this, I would use T's and H's. So we had our tail, tail, head, which is this one. So our whole sample spaces are all the other things that we could narrate, but we've established that they're all going to be 3 things long, and they're all going to be made up of H's, and they're going to be made up of T's. So a convenient way to make sure that we're not forgetting anything is to make a tree diagram. So very quickly, I could think about what are the actions I'm taking in my chance experiment that I need to narrate, and what are the possible outcomes for each of those actions. So my action number 1 would be my first coin toss, and I can get a head or I could get a tail. My action number 2 would be the second coin toss. Now, because it's unaffected by our first coin toss, it's still going to be heads or tails, heads or tails. So that leads us to 4 possible outcomes, and each of these 4 are going to spawn 2 more possible outcomes. So this will spawn another option of heads, tails, heads, tails, heads, tails, heads, tails. And we'll see that we have a total of 8 possible outcomes if we count them, whereas each branch is going to be 1 possible outcome. And then the next one, head, head, tails, like this. So as I read down, I am going to get those outcomes in order. Now, you'll notice that because we always have the same options at each of our choices, this is going to create a way that we can easily count how many things we should have had. I had 3 actions with 2 choices each. So for each action, I had 2 choices. So 2 times 2 times 2 is a total of 8. Because we see the first action that we had, it spawned 2 branches. Now each of those branches spawned 2 more branches. So those 2 got multiplied by 2. So now we had 4, and each of those 4 branches spawned 2 more branches, for a total of 8 branches in our sample space. So you want to find a method that's going to work for you. If you're computer inclined like I am, I like to pretend I'm going through a nested loop, and that's how I make my sample spaces. If you don't know about nested loops, tree diagrams are a great way of doing it. The point is you want some sort of ordered method to do it, and not just randomly thinking up all the different outcomes that you can. And another side note to this is, so I said we could shorten this to tails and heads. This is fine where obvious. If you're doing a question and it's about someone buying coffee, cupcakes, or croissants from Tim Hortons, you should probably make a different letter for each of those and make a legend. So the rule that for my classes that I like to talk about is, don't treat me like I'm dumb. I can tell what the T and H is supposed to represent, but don't make my life hard either. So use common sense when you need to decide if you have to give a legend or not. The other thing we want to note is, remember that I was narrating something that was happening in sequence and in time. I was calling out each one individually. So even though in theory the outcome heads, heads, tails had the same number of heads and tails as heads, tails, heads, I actually said something different. Because it would lead to a different narration, it's a different outcome in the sample space. If you can't hear me say something different, they're the same outcome. So we'll see an example of that coming up, but hold on tight. We'll do a few basic examples still. Okay, another one we might see is looking at decks of cards. So in a deck of cards, for those of you not familiar, they all have different suits on them. So there's 4 different suits. There's hearts, there's spades, there's clubs, and there's diamonds. So if I was doing a chance experiment where I had a deck of cards and I had to pick 2 cards and check what the suits were, so something that could happen, I could get a spade and a diamond. So what I narrated out loud was, I got a spade and a diamond. So my outcome that I'm going to get is going to look like this. SD. I got a spade and then I got a diamond, which is different than if what had happened was this. I got a diamond, I got a spade. You hear me say something different, that makes it a different outcome. That's why we also have the outcome diamond, spade. Order matters when we are doing sample spaces because it is literally something different that had happened, and we need to keep track of that. As long as they're distinguishable, they belong as a different outcome in our sample space. Now we can use that rule for how many things there were. At our first action, we had 4 choices. So we had 4, and then we had our second action was pulling the second card. So we had 4 choices. So 4 times 4 is 16 outcomes in our sample space. The first branch started 4, and each of those 4 branches spawned off 4 other possible branches. For 4 times 4 is 16 outcomes. One more, very common in stats, is dice rolling. So we can imagine, again, we're rolling 2 die. Roll it like I'm flipping a coin. So I get a 3. Let's roll this die again, and then a 2. So I narrate that as I got a 3 and I got a 2, which tells us that we should be getting outcomes that are 2 things long and are made up of the numbers 1 through 6. And if we look at the sample space here, we'll see that we have all of those things. So we have, for each possible outcome, notice how we have, for this whole row, they all start with 1s. For this column, they all end in 1s. So this is actually a nice way of finding sample spaces when you have only 2 actions. You can kind of pretend that you have this outside graph here. 1, 2, 3, 4, 5, 6. And then you have this row, 1, 2, 3, 4, 5, 6. We can see where they match up. So for example, here and here matches up to the number 4, 3. So we can make our sample space that way. Again, 6 choices times 6 choices for a total of 36 outcomes in our sample space. Now, I made a point of saying that we have things that are 2 things long, and these are the things that they could be described from. Now, this would be very important when we have really large sample spaces. Writing out 36 things is kind of annoying when you get to things that are thousands, millions, billions. You're certainly not going to list your sample space. So as an aside, oftentimes what we do is we'll use set notation to describe them, and it's going to look exactly like I was just saying. So for example, when we're using the dice rolling, remember we said everything was 2 things long and they came from the numbers 1 through 6. Well, that's basically what we're writing here. So our sample space is equal to the set of, so that's what these brackets are doing. It's the set of, we want to think our set of x1, x2 pairs. This straight line here in math represents such that our x1, x2 belong to the set of the numbers 1 to 6. So it's a convenient way of saying there are 2 number pairs where those 2 numbers come from the set 1 through 6. So large sample spaces will often describe them in set notation instead of listing them out for us. All right, so we're going to do an example now that is an example of things that, even though they look the same, if I were to narrate them, they would be the same outcome. So in this question, we have a fair 6-sided die. It has 3 faces that are painted blue, 2 that are red, and 1 that's green. I toss it twice. I want to find out what my sample space is. So I can pretend I don't have a die with these faces, but I can imagine that I did roll it, and we can think one thing that might come up is I might get a green face, and I might get a red face. So I think what would my outcome be? My outcome would be GR for this. So this tells me that my outcomes are going to be 2 letters long, and they're going to be made up of the letters B, R, and G. So we can eliminate all of these options where they're not 2 letters long. So here we have the option of A or B, and we know that order is going to be mattering. That's the difference. We know that if I had drawn this red, green, and I narrated that, I rolled a red die and a green die, I hear something different than when I said I rolled a green die then a red die. So there are different outcomes in our sample space. So this is going to be wrong. And our answer is going to be E. There's another option that we didn't actually eliminate that we just want to think about for a second. There are actually 3 faces that are blue on this die. So we can imagine that one outcome that I get could be blue and blue. But the first time I roll that, say we added a number to the die. So say we actually numbered the faces. Blue 1, 2, 3, red 1, 2, red, green. So I might have 1, 2. So say we actually just defaced our die and added these numbers. So another one that I might get is I might roll the 1 and get the face that had a 2 and get the face that had a 3. But when I go to narrate the experiment, the only thing that I am saying out loud, because we're keeping track of the color, is I rolled a blue and I rolled a blue. I rolled a blue and I rolled a blue. You heard me say the same thing. So even though there are multiple faces that will lead to BB, it only appears the one time in my sample space. We only get a different outcome if we can actually tell the difference given what it is we are keeping track of. We can't tell the difference between 1, 2 blue and 2, 3 blue if the only thing we're keeping track of is the color when we go and narrate out the experiment. Now, there's one other type of sample space that I want to talk about, is when our actions at subsequent actions are going to be affected by what we had done previously in the experiment. So let's bring up a question. Suppose I have 2 nickels, 1 dime, and 1 quarter. I select one at a time until I've picked both nickels. What is my sample space? So here, depending on what I pick, it's no longer going to be available at my next opportunity. So if I pick the dime on my first action, there's no longer a dime to pick on my second. So when we make our tree diagram, we're going to have to keep this in mind. So we can think my first action, when I haven't done anything, the things that I might pick out are a nickel, a dime, or a quarter. Now, yes, there are 2 nickels, but for practical purposes, we can't distinguish between them. So we are going to have only one end there because both of those nickels lead to me saying nickel. Now, when I go to take my second action, when I've picked a nickel, so we're looking at this branch, I still have a nickel, a dime, and a quarter left. So I have all of my options still. But when I go to my next branch and pretend I've already removed a dime, what's left? I have 2 nickels and a quarter. So what could I possibly pick? I could pick a nickel or a quarter. And when I go to that third branch, I've picked a quarter. What's left? 2 nickels and 1 dime. So what could I possibly do? I could get a nickel, or I could get a dime. Now, when we go to add in our third option, so if I had that nickel as being the first one, well, at this point, I would be done. I would stop. I have no more to pick. I've done everything I had to do. I've picked both nickels. So my first outcome would be nickel. But my next branch, nickel, dime. So I picked a nickel and I've picked a dime. What's left? A nickel or a quarter. So I could pick nickel or quarter. If I picked a nickel and a quarter, I would have a nickel and a dime left. The next one, if I picked a dime and a nickel, I would have a nickel and a quarter left. If I picked a dime and a quarter, the only thing left would be my nickels. If I picked a quarter and a nickel, I would have a nickel and a dime left. And if I picked a quarter and a dime, I would only have nickels left. So let's see which ones have ended. So if I look at this branch, I've picked nickel, dime, nickel, so that's done. I've picked both nickels. Same thing here, nickel, quarter, nickel. I've picked both nickels, I'm done. Here, dime, nickel, that's done. Dime, nickel, quarter, no. Dime, quarter, nickel, no. Quarter, nickel, yeah, that's done. Then quarter, nickel, dime, quarter, dime, nickel, those aren't done. Now, at the time I get to my fourth coin, this is easy. It's whatever's missing because I only have one left to pick. And we should know that it has to be, without even thinking about it, the nickel. How do I know that? Well, if there was a dime or a quarter in there, that means that I had already picked 2 nickels and I shouldn't still be picking. So it's a little cheat for us for this last one. Now, because we've picked everything, we obviously have both nickels. So we get our sample space by looking down these branches. So we had nickel, 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 dime, nickel, nickel, dime, quarter, nickel, nickel, quarter, nickel, nickel, quarter, dime, nickel, dime and nickel, nickel, dime, nickel, quarter, nickel, dime, quarter, nickel, dime, quarter, nickel, nickel, quarter, nickel, dime, nickel, quarter, dime, nickel, nickel. And we'll note that we couldn't have counted this out ahead of time because we didn't have the same number of choices. Each branch didn't spawn the same number of branches as everything else, so we're not going to be able to use that technique here. You can see this is much easier than trying to think off the top of our head and just come up with as many solutions as we can until we get to the end. So you want to think, if I say something different, it's a different outcome in my sample space. Make one example in your head, or if you need to physically do it, go ahead and do that, just to get a sense of what the sample space should look like. Find some sort of ordered way of doing it. Don't just randomly guess, whether it's a tree diagram, nested loops, or with two outcomes, we could do the little square thing that we did. Whatever you do, you want to make sure that you have a technique to make sure you're always going to come up with every outcome in your sample space. And that is how we make our sample spaces, our list of possible outcomes. The next thing we're going to look at is how do we get the probabilities for them.